Regular functions are kind of limited when it comes to graphing. Remember the vertical line test? How you can test if a graph is a function by checking for any 2 points on the graph that have the same x value. What if you want a graph like loops or circles or something like that, though? That's where parametrics come in. As a refresher, parametric equations are equations that can be graphed, but they're represented by 2 equations instead of 1. An equation for x and an equation for y. Both are in terms of some third variable t. These aren't like a new strange x and y, they're the old familiar ones, horizontal and vertical position of a point on the graph. You can graph a pair of parametric equations by plugging in various t values into both of them, getting coordinates out of it, and all of those coordinates together make a graph. This allows us to break that vertical line test from earlier. We can make roller coaster graphs and spiral graphs and circles and these graphs also have tangent lines and slopes and arc lengths and all of that, calculus stuff. Finding those things, though, requires some new calculus, since our earlier stuff has been pretty dependent on it being a singular, regular function. So, allow me to introduce you to a few formulas. Here's the formula for finding regular old dy dx for a parametric equation. Dy dx is still the slope of the tangent line, but dx dt and dy dt are the derivatives of those equations for the graph. Notice that if you thought of all of these d variable pieces as independent variables, it's kind of like the dt's cancel out. As an example, let's use these equations and say we wanted to know the equation of the tangent line, specifically when t equals 4. First, the tangent line is still a line, so things like y equals mx plus b as a formula still apply. And since m is the slope of the tangent line, it's still dy dx. To find dy dx, we need to know the derivatives of both x and y. This follows your normal derivative rules. Then, we use the formula, dividing them, giving us dy dx. We can use this derivative to find the slope that we mentioned before. Since we know the slope now, we can update the equation for the tangent line using this value. We can find b in a familiar manner by using any point on the line. We know the point where t equals 4 is on the line, so let's use that. And there's our equation. You can see that it's definitely a tangent line. You may be asked to do a couple of other calculus things with parametric equations, so let me give you a couple more formulas. For instance, when you need to take the second derivative, you can take the derivative of the derivative like normal. However, make sure you also divide by dx dt again. Another tricky one you might run into is arc length. Remember the arc length formula? For regular functions, that is. For parametrics, most of it's the same. But instead of 1 plus the derivative squared under the square root, it's both derivatives squared and added. Notice that since it ends with dt, the limits, a and b, are t values, so watch out for that. There's all sorts of integrals you can get from these, so try some out, challenge yourself. You have all the tools, now you just gotta use them. Good luck!